let's see, record mode. We can hide this. Hide floating controls. The things I really like that. Let's see, I'll just go to a new thing. And right, so just try to it's not muted, but if you're just not really any time, spit out if you have a question. And then for the question thing, like just and if things are going crazy, just say, I see. And so I guess you can hear, someone said you can hear, and I'm going to try to do some notes on this. It's upside down, so I can't really fix that. But basically, it's from my phone and should work. Might be weird. Anyway, it's this is the paper. Still connected. Why not? Sorry, okay, I'm back. Somehow the internet messed up here. Well, it's looking good. That should shrink that right there. All right, so this is the homework. The paper, it's the paper and there's two other papers that are referenced in that paper. So it's the paper that they put spherical nanoparticles into this pyridine polymer, right? Which is, I can just get a picture of this this thing. So it's got a nitrogen group on it, which has kind of a negative charge. The neighboring negative charge charge. So kind of the actual charge. It's got two, which has a cyanol group on the surface, which is negatively charged. Kind of weird, but that's how it is. Maybe I'll flip it up. That won't work. Anyway, the other one's alumina, which has like a weaker charge. Usually alumina has a positive charge on the surface, but depending on the pH, it can be negative or positive. So this is like weak surface charge, and this is fairly stronger, like a stronger surface charge. So it's expected that the silica and the silica nanoparticles, I think he has like 20 angstrom, and the alumina are like 6 angstrom, I think. So they're pretty small particles. I think it's angstrom. Is that angstrom or nanometer? Let's see. But 20 nanometers, 6 nanometers. Micron is 1,000 angstrom. A hair is 50 of. It's small, but it's so 200 angstroms about what a polymer chain, a normal 100,000 has has that kind of size, about 200 coil, and these are smaller. This is smaller. And that's important for so looking at transport of these particles in this P2 vinyl pyrrolidine polymer in that polymer, right? So, and they've got a fairly incredible molecular weight range, 1,000 to 1,000,000. So they have a nice molecular weight range, and it's a fairly narrow distribution molecular weight. So it's a completely model system. These are spheres mixed in a huge molecular weight range in it. So this work. It's unfortunate. If you have the Stokes-Einstein equations, we have the diffuse hydrodynamic radius viscosity, right? And the viscosity goes with the molecular weight to the 3.4 if it's entangled. Log viscosity, log molecular weight, going up power 1, that goes 3.4. Right. So you have this 3.4 and you park it there, and the RH would be equivalent spherical diameter, and these are spheres. So you just say that's the sphere diameter. So that's fixed, and temperature is fixed. So you should get that the diffusion coefficient like the weight to the negative 3.4 power if it's just the viscosity. So if you look at this plot, so they have decades. If it's a power law, you expect like 3 decades. So 1, 2, 3.5 versus 1 decade, which would give you a slope of basically like what the blue line is. So this is following just Einstein-Stokes equation using the entangled polymer molecular weight dependence of viscosity, this straight line. It's like 3.4 by 1 decade. So that's the power law of 3.4. So anyway, so that's good, I guess. So that means that's just Stokes' law for polymers. And then there's a transition. So they're mixing these beads into. So all of a sudden they get a constant value. I switched from the wireless here to my phone because the wireless is not working. So hopefully that'll work now. 2 glitches. All right, so rid of that too. All right, so hopefully it's still there. So all right, so the Schweitzer, this is for simulations, and you got
So sorry, we can't see your screen.
okay, thanks. Let's see if I can fix that. Uh, thing I'm looking for. Let's just say. Okay, so share. Right, it's not sharing. All right, thanks. So Can you see it now?
Yeah, thank you, sir.
Sorry about that. Uh, hide that, hide this. Right, hopefully my phone will be more stable than their wireless. Go back to this guy. Right, so one thing, so this is a simulation he did, and he's showing, all right, so there's kind of a look at power 3 and power 1. So it's kind of a power 3, like Stokes' law for the red one. And then he shows that tail over to flat. One thing is that the difference between Stokes' law, which would go down here, and the flat part is 2 decades in diffusion coefficient. Right? If you go back to the whiny thing, so the difference here is like kind of more than that. It's like 3. I mean, at this end, it's like 4, which would be 10,000 times faster diffusion. So that's a pretty significant change. In the Schweitzer simulation, it's kind of a smaller change that he sees. So that's one thing that's different between this simulation and what they have. Schweitzer did that, and they also did experimental, where instead of comparing, so he just divides by the Stokes-Einstein. So when he has 1, he's getting Stokes-Einstein, and then the deviation. His deviation's about 10, like a factor of 10 when he gets over here. So seems like they're seeing quite a bit stronger dependence out here than what they were predicting in the theory. So as the theory goes, so there's Schweitzer, the first Schweitzer has a pretty good description, almost like a textbook about diffusion in polymers, particle diffusion in polymers. So there's an issue that if the particle is much larger than the polymer chains and much larger than the entanglements, then you get basically Stokes-Einstein behavior. And if the particle gets to be on the order of the polymer chains, then you get kind of modifications to the Stokes-Einstein. So the modification is that you take the Stokes-Einstein equation, and instead of using the size of the particle, size of the sphere, you have to include this idea of oh, he shows it here. So he includes, like, he takes the sphere and he says some of the polymer chains stick to it. And then the particle just carries those chains along with it. So the actual radius is going to be a larger radius. So the Stokes-Einstein is going to have a modified larger radius. That'll be the radius of the sphere plus the size, 2 times the size of the coil. And the coil, in other words, 2 times the radius of the coil would give you this extra size to it. And that should reduce the transport because it's a larger particle. Then the viscosity, they modify using another Einstein equation. Let's see, this is the whiny paper. They give that equation in the text here somewhere. Let's see, it's just you're just going to add here. So you're going to take the viscosity of the polymer, and then you add in this. So the first 2 terms is called the Einstein equation for viscosity of like a mixture of a solid, particles, and a liquid. So it's just a displacement law. Like you're adding in, you're kind of removing the say your viscosity is going to be this is upside down. So you have the viscosity, you have velocity, fixed bottom, then you're going to have this velocity gradient. So gamma dot is the change in velocity with respect to y. Yeah. So if you add in particles, say you just got rid of some of this y, like you just add bricks to it, that would make it, but you're still gonna have the same fixed viscosity. So you have a higher effective shear rate because you have less. So you say you just displaced it. So that kind of displacement, you can just use a constant times something. And this 2.5 Einstein did this for spheres. So for spheres, it's 2.5 because spheres aren't bricks. When they pack, they have like holes. So the 2.5 accounts for how the excluded volume of spheres. So this is just a displacement law. So Einstein wasn't very proud of this. It's a really simple law. And then Guth Gold came up with a modification for kind of filled polymers like carbon black in tires, rubber. And they added the square term to account for some like these particles can kind of interact with each other. So there's an effective size that they have. So you have to kind of consider the binary interactions. You have a volume squared term. So this is kind of a well-known equation for composites, for viscosity and for modulus of composites. Anyway, so that's the polymer viscosity. So this is a larger viscosity because you're adding in these other positive terms to it. So that also reduces it increases the viscosity, so it's going to reduce this diffusion coefficient. So this number gets to be higher. So they've got these two modifications to account for, and it seems to work surprisingly well, given that the particles they're using are smaller than the radius gyration of the polymer. So you wouldn't expect this to exactly work because your particles, or you have your chains, so the viscosity of the chains, and you have these little teeny particles in it. And you're saying the bulk viscosity is going to be the particles displacing the fluid to make the viscosity higher, but you're actually looking at the viscosity within the region near that little particle, which seems to be that it wouldn't necessarily be modified by the other particles. Anyway, nonetheless, this equation works well for these samples. I think the blue line is like a calculated Stokes-Einstein using the parameters of the measured parameters that they had. So basically it works pretty well until you get to this point here. We're at very high molecular weight. So it's over 100,000, approaching 1,000,000. You have the very small particles. So particles smaller than the size of the chains of the entanglement network. And in that case, you just get a constant diffusion coefficient. It doesn't depend on the molecular weight anymore, meaning that it's not dependent on Stokes' law anymore. Stokes' law fails, and the reason that it fails, so the reason it fails is described by Schweitzer kind of so the first part is where there's no interaction. In the introduction, this whole page and up to this paragraph is when there's no interaction, which he says it's well described already, so he doesn't need to talk about it. And then the second part of this, and what this paper is about, is when you have strong bonding between the polymer and the particles. And then he says there's various, depending on the size of the particle, molecular weight of the chains, and the size of the chains, and the bonding interaction, you can get 4 different mechanisms going on. And one is the mechanism is this bonding where you have a core and shell, he calls it. So you have a bonding of the chains. That increases the radius. Then you also modify the viscosity, and that's why they get a perfect match. That's the core and shell model. The other model he talks about is a vehicular model, which is something they cooked up. So it's basically the particles are very small. So in the case, basically in this region, we have very small particles, the particles, and then the molecular weight is high. At that point, the bonding between the particle and the polymer, so he says fusion's a dynamic thing. So there's a time constant. Saying there's a time constant associated with the chain sticking and de-sticking from the particle. In other words, all these chains have some kind of tension on them. They'll eventually be released. And there's a certain resonance time that the chain will have bonded to the particle, and then it will on average release in a certain time tau. That's the tau desorption. Right? He shows kind of here the green chain somehow desorbs. This is supposed to show the chains attaching and detaching. And then, so the vehicular model, depending on the size of the particles, the size of the chains, and that time constant, and the time constant for the polymer network to relax. In other words, a viscoelastic time constant. The thing where we see the viscosity, let's see, where is the top here? Well, that's hard to write upside down. The thing where we see, and this is upside down, so we see like gamma and viscosity, gamma dot, and this is log. And then it's going to tail over to a power law fluid, the decay and high shear rate. And there's some 1 over that gamma dot gives you kind of a viscoelastic time scale for the thing. So there's that time. There's the time that these little particles are. There's a time scale of these things attaching and detaching. So you're comparing those two time scales. And if this time scale beats the viscoelastic, in other words, if this time scale is longer than the viscoelastic one, then the chains will carry the particle with them for a certain length of time. The chains diffuse faster than the particle. I mean, that's an assumption of it. So they'll carry the particle along with it a little time and then drop it off. So it acts like it's carrying the particle on its shoulders. So some of these particles, like in the experimental part of this, and this guy, this Sokolov has done work with these sesquioxane silicas, which are basically silica SiO2 cages, and they're maybe of 20 to 50 atoms. So they're very small particles. They're beyond nanoparticles. They're really molecules. Basically, they can be used kind of as fillers. There's no industrial product doing that, but basically you could. Anyway, so this thing uses those sesquioxanes. So they are so small that when you look at that model, like this isn't even really, like they really are as small as the Mur units of the chain. So that becomes kind of a realistic picture. Most of these filler particles are going to be much larger, right? And also, anyway, so yeah, I didn't mention, so Schweitzer is kind of a famous, he's like one of the top polymer science people. He's at Illinois. And then this Sokolov is at Oak Ridge National Lab. And then the other people, I don't know, but I think they're all working with these two. And then the original paper we're looking at, Winey's at Penn, and this is a grad student, I think. So basically that's kind of the framework that they're dealing with. They're trying to see this transition. This paper is good in the introduction of the past, and then it kind of goes into this new theory, these two modes, and then he has like too much detail of it, and we don't really care that much about the math. The point is that depending on the size of the particles, the time scale, this attachment detachment, and then the viscoelastic time scale, you can come up with these. I think there's 4 different modes of transport that you can have. So one, I, and I guess there's 3 different ones. Right. So Winey gives a nice little half a paragraph for each of them. And then Schweitzer in this paper is going to give like a page each with a lot of math. And the thing that's important is that there is one regime where this transport doesn't depend on the molecular weight anymore. It only depends on this desorption relaxation time, which is fixed. So that's a chemistry issue. And again, silica has a strong, so it's got a long relaxation time. It takes a long time to break apart the bond between the polymer and the chain. And alumina has a weaker one, or none. So basically that time of desorption is shorter. And because of that, and because the alumina is smaller, so you get a different Stokes behavior, you basically can reach this plateau in alumina and not in silica. That's the theme. So the reasoning why it goes flat is because it doesn't depend on the viscoelastic time scale anymore. It only depends on this desorption time scale. All right. So anyway, it's kind of absurd. I mean, you can argue, all right, what's the error bar on this point? And then, I mean, these 2 points, you could almost say they're on the line. This point isn't on the line. And then what's the error bar on that point decides the whole thing about do you have this tailover or not. In other words, if I cover this point up, do I see that behavior? That's a question. So you should always ask yourself, like people put in lines to mislead you, right? It's a way to lie about things. So I mean, everyone does that. So I'm saying I do that, but basically they have a belief system and they draw a line and oh yeah, there it is. There is a God, because that happened. But that isn't necessarily statistically relevant, right? So whether you believe in their God or not, like you have to cover up some of the evidence they have and say, is it still true with just those weak points? And so anyway, nonetheless, they seem to have a pretty convincing argument, more or less, on this. So what they're doing, so how they measure it, all right, so I should say too, there is nobody in industry that cares about the diffusion coefficient of a particle in a polymer because in industry, you slop the stuff together in a mill and you grind it up and mix it until it mixes. and then and then it's stuck. So there's the kinetics of it are induced. So this diffusion coefficient, like when we derive Stokes' law, we use KT for the transport. That's why the equation has KT here. This is transport driven by thermal random motion, like a random walk, right? So in industry, it's not random walk, it's ballistic. Like you're ripping the things apart in straight lines. You're putting shear on it and you're forcing it to be dispersed. And then you're hoping that once you stop mixing it, the viscosity is so high that the viscoelastic relaxation time is way too long for it ever to go back to the state that we want to go into, which would be all the carbon black at the bottom and all the polymer at the top, which would be not reinforced, right? So anyway, so what value this equation has in that context is questionable, right? That's part A. Part B, if you look at this is the kind of material you're talking about for like a tire, which is the largest produced nanocomposite, right? So these are nanoparticles of carbon black. They aren't, so they kind of have spherical primary particles, but they're arranged in these bonded aggregates, right? Then the aggregates are a concentration level that they interact and form a filler network in the system that gives you the strength that you're looking for, actually the tear resistance. The main benefit of this is that you go from a pencil eraser that falls apart when you rub it on the paper, and if you made a tire out of that, it would go about 100 miles before it ripped apart, right? Into something that's so tough that you can drive it for 60,000 miles. Right. And you take a knife and try to cut a tire. They always show people stabbing a tire to let the air out. It's almost impossible to do that. That this stuff is so tough you can't cut it. That's because of this network of filler particles. So these monodisperse kind of dilute spheres have nothing to do with that, right? And also the kinetics of it is not governed by thermal transport. The kinetics is governed by mechanically forcing it to mix. Right, you put it so there's a lot of problems with this. Nonetheless, so there's a long history of people looking at diffusion and polymers and arguing that it has something to do with this, right? So in reality, it doesn't. So it becomes like almost a self-feeding. So you have to kind of look at these things critically and say, like, this is a self-feeding thing, and the more work. So anyway, so they've developed techniques to look at to measure the diffusion coefficient, right? And one method is this. So it's shown in here. So if you have so you have particles in a solution and they're kind of thermally vibrating around. So if you look at the kind of the position of the particles over time, you get a jagged curve. If I can draw that, but why to quick time disappeared here. Anyway, so you get a jagged time, and if you take positions on that, you can get a correlation function. So at short distances between 2 points, you can have the same value. If you go to longer distance between the points of a noise pattern, they become less correlated. So if you take the dot product of those, that basically decays to zero. There's no correlation anymore. So just looking at a noise pattern of particle motion, you can do it with a video camera or you can do it with light scattering. Doing a correlation function of that noise pattern of the particles moving gives you these decays, and if you fit that with an exponential, you get a relaxation time, and that'll give you the diffusion coefficient. Right, so basically, short decays on this correlation function give short relaxation times and large diffusion coefficients. And then these are smaller diffusion coefficients over here that have longer relaxation times. It takes longer for it to decorrelate. So, okay, so there's that technique to doing it. And this can be done with light, with X-rays, or with neutrons. Here they're doing this with neutrons. And this is the sesquioxane here, the silica. So these are SiO2 cage, and it's got some organic group on the surface to interact with the polymer. So basically this is not exactly really a particle, it's more like a molecule. It's like a big molecule, right? So sesquioxane is something people have looked at. That's what these, in the second paper, the Schweitzer, that they And in this paper, they're not doing that. In this paper, it's kind of a in the Winey paper, they're doing kind of a brute force mech way to get the diffusion coefficient. It's a little bit older. So basically, they spin the polymer onto let's see. Let me see what happened with this guy. QuickTime didn't work or something. This should work theoretically. Um, to my phone. See what happened. The phone stopped doing it. Okay, that's good. So flip this over. So yeah, so the one way to do it, you have a say you shoot a light in, you have your stuff, the particles are moving by KT, you pick up at an angle. The signal you get at that angle is going to be a noise pattern. I can say like at that and that, the correlation between those is 1. At that and that, the correlation between those is 0. So if I plot the correlation with time, it's going to be 1 at short times and then decay to 0, right? And I can fit that with exponential minus time over tau, some relaxation time, and that relaxation time will give me the diffusion coefficient. Like 1 over tau will give me the diffusion coefficient, more or less. Anyway, so that's called dynamic light scattering, quasi-elastic neutron scattering, X-ray photocorrelation spectroscopy. So you can do it light, neutrons, X-rays, more or less. And you just get the diffusion coefficient from that. The way Winey does it is they spin coat polymer onto a surface. And then they spin coat a polymer with particles in it onto the same surface. Then they spin coat the polymer onto the surface again. And then they take that and they bake it in an oven, right, for a certain length of time, like 1 day. And then they're gonna look at the original one and the 1 day one, and then they're gonna shoot an ion beam at the surface. So I think it's krypton or something. And they look at the things so they ablate, meaning they're gonna blow off whatever's on the surface. Then that whatever blows off, they put into a mass spec, which gives you number versus mass. And as they ablate, it ablates, the time of ablation will probe deeper and deeper into the surface, and they can get this, so they can pick out the different elements like SiO2 in it, or Si and O2, and then they can plot SiO2 versus the time they annealed it. So you can see this is a much longer thing to do than sticking something into a DLS and getting the noise pattern and getting the correlation. So but in the end, they're going to get the same kind of thing. Like they're going to fit that with this fixed diffusion law, which gives them the diffusion coefficient. They're going to fit this profile. So the profile is basically a Gaussian profile they showed in here someplace. That's a profile they get. So they're blasting away at their surface, and then they find, oh, there's silica, and then they're going to say, oh, there's more, and then they get to the layer that they put in of silica, and then it's going to go down at the other side. So it's diffusing. It would have been a spike for the original one, then it broadens out with time due to the diffusion of the particles in the thing. Then they can, from that, they fit that curve with this kind of, I guess this ends up looking like a Gaussian bell-shaped peak, and they get these two. Error function is an integral of a Gaussian. So this is kind of an integral of Gaussian function. And so they get the diffusion coefficient from that, and they can plot the diffusion coefficient as a function of whatever they want. The ratio of the polymer chain size to the particle, and they see that deviation at the high end for the alumina. And then again, there's like no error bars on this. That's one problem. You can see there's quite a bit of error. So the error bars would be large. So wondering if that's real or not. You'd have to kind of get error bars on these to really say. Anyway, so that's the gist of what they're doing here. You can look at it. It's not the technique isn't that important. I mean, you should kind of have a rough idea what they're doing. Um, Being able to look at this and kind of critically look at it is important. And like from the point of even from the starting point of like why are they looking at diffusion coefficient? You can say like this goes back a long time previously. So this guy Ed Kramer at Cornell, Winey had something to do with him. Then he went to Santa Barbara, and I think he died a few years ago. But anyway, he did diffusion, right? So he handed off to Winey and some other people this idea of diffusion coefficient that was important for polymers. And then like DeGennes picked up on that, the guy that won the Nobel Prize, and he Schweitzer mentions the DeGennes theory on transport of diffusion. So that popularized it even more. So it's like everything's piling on top. This guy does it, that guy does it, so I have to do it too. And more or less that's where we are. Like people are chasing after the diffusion coefficient when no one in industry ever asked for it. No one said like we need the diffusion coefficient. So it's kind of like, yeah, it's good to have Stokes' law and it's useful for polymer theory. And this seems to show some things about how the viscosity behaves with molecular weight and how it carries into diffusion coefficient. We have to keep in mind, like, there is no use for this at all. Like, probably no one has ever used a diffusion coefficient in an industrial process, with the exception of maybe microelectronics, where you're doing thin film coating and you need to know transport of something in it. I don't know. I mean, it's possible you could use it, but really, this is a lot to invest in to do to get something that no one asked for, right? Exactly. So anyway, so that's a typical physics thing, though. So anyway, so it's important to kind of keep a critical view of it. So so the homework. Any questions on this stuff? Like it's a lot. Like sorry about the technical. I brought a thing to hold the phone, but I left it in the car. And then by the time I realized it was too late to do this, but anyway, hopefully that's all right. Um, so let's see. She talks about like Rouse. So Rouse transport is the thing where viscosity is proportional to molecular weight, and then also you get that the relaxation time, which is 1 over the diffusion, goes with molecular weight squared, and then reptation time is the time to kind of relax the entanglement network, and then that's going with molecular weight to the power of 1, right? So, oh, go ahead. If you have something, just say. Go ahead.
Yeah, sir, I didn't get a explanation between the diffusion coefficients in the study and then the industry. Like, I don't
Yeah,
get.
there is none. There is no relation. Like no one wants diffusion coefficient in industry. The only time people want it in industry is going to be something like where you're doing something pretty specialized. Like when you etch a silicon wafer to make microelectronics, you put a coating of PMMA on the surface, like plexiglass. And then you irradiate it with UV to get it to polymerize. The parts that don't polymerize, you wash away with a solvent, and then you'll coat it, and the polymer part will block the deposition of, say you're doping it with phosphorus or something to make it a N-type semiconductor or whatever. So you get a PN junction so you can get different electronic components that way. Then you want to know like the diffusion coefficient. People use the diffusion coefficient to describe that, like the profile, how sharp of a feature could you make in the microelectronics, that type thing. But really, like most people, like your co-op jobs, if you've worked in this, like you're just pouring stuff into a mixer or you're extruding it, or so the thing is kinetically driven by the machine. It isn't, you're not looking at KT diffusion to decide what happens, right? You're going to either extrude it faster or slower, right? The chain relaxation and the viscosity stuff is important. I'm just saying that there's a lot, like you can go to a meeting, it'll be a whole meeting just on diffusion coefficient and polymers. You know what I'm saying? So basically, there's a long history of looking at it. It's hard to see like that it's so important that it merits that. So, but anyway, nonetheless, like it's still here. It isn't going away. So I'm showing you something from this year, kind of last fall. they're doing exactly that. So that seems to be like still a prominent, they're getting a PhD in diffusion coefficient. So does that answer that? I'm already
Yeah,
against, I'm giving you a paper for it.
thank you so much.
Yeah, you can make up your own mind about it, but basically,
Yeah,
you have to be a little
I don't know
careful.
if you can, I think you talked about the tires,
Mhm.
like the way tires are manufactured.
Yeah,
I can get that.
yeah, like this is kind of a micrograph of what a tire might look like inside, like a clean one, you know? And that's kind of that's the major nano composite in industry, you know, and the kind of things that you touch. It's a huge impact of adding carbon to the polymer. I mean, you go from an item you could use it for raincoats or something, but you could never use it in any kind of a conveyor belt, tires. Like you can't make a car without a tire. Right? In the original days, they had like steel and wooden wheels on carts, but you can't drive that at 60 miles an hour on a highway. It would rip apart, right? So the only way that you can have a car that doesn't run on rails like a train, right, is with rubber. And the rubber is only functional if you have this kind of nanocomposite. So it's pretty vital to a lot of things. Also, like conductive flame retardants will look like this when you add them to polymers. Conductive things for packaging, you know, for electronics packaging. Um, Basically all over the place, but it's never this. It's always that. It's always going to look something like this, not these little independent particles.
Okay,
So yeah, so
okay, that makes sense.
yeah, the physics and the engineering are disconnected here. And this paper is kind of maybe I don't ask questions on that, but basically. All right, so let me just go any other things or just jump in if you want. Thanks for doing that. But all right. So it just cut me off. Don't worry about it. But so anyway, all right. So anyway, I go through a little bit about that, whatever my opinion on whatever is. So and then I just say like do the two, take Einstein's so we had Einstein's let's see, paper, whatever that is. It's kind of here. So and I went through it in the notes. Mm, kind of here, right? So this, I'm just asking you to kind of go through this and get this, just do the same thing. Just get this thing and say that it's related to that. So the diffusion's in time and because the average position diffusion is also zero, the particle can move left or right. So you get zero average. You need to look at the variance, this the root mean squared distance traveled, which is the variance. And that following this Einstein thing gives you the diffusion coefficient times time, right? Meaning that if you watch something move and then you see it time to the 1/2 power, right? That means it's diffusion. If it's time to the one, that's ballistic. That means a bullet, you shoot it, it's got a velocity and then time. So in that sense, the diffusion coefficient is acting as a surrogate for velocity here. Like a square root of diffusion coefficient is kind of a velocity for this, more or less, right? But it's going to go with time to the 1/2. Um, and then, uh, and then, yeah, so time, if you say you have time steps, so the total time is going to be the total number of time steps, so that would be like n. Like fixed time steps, like in a computer simulation, like a dynamics, you do time steps. So the time you have, it's actually a series of steps. It's actually n. And then r squared, x squared, or distance squared, root mean squared, or roots are just the square, mean square. And then 2D correlates with the Kuhn length, right? So it's kind of like there's parallels between these two. The math is the same. You could put the Polymer coil, you could do the diffusion. That's the first question. First question is like, just do that. And then, oops, here, just do that. And how does it relate to that? So n is time. If your time is in steps, then you end up with n, and L squared is 2D. And then Stokes-Einstein, so do the derivation that I did. Just go through this on your own, you know, to justify in your brain that this works. I kind of did it with a series of steps, but the steps are in here. Basically how you get this equation. right? So that should be, going through that might help you kind of think about it. And then, what conditions? This is observed for particles in polymer composites. So, the conditions, the Schweitzer in paper A goes through the conditions where you see Stokes-Einstein. He says like large particles, basically. Large particles compared to the size of the polymers, and large particles compared to the size of the distance between entanglements in the polymer network. And then he goes through he gives three things in paper A where this would be observed. Where is that? Da, 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 the three regimes where you'd see Stokes-Einstein. A, particle size is big compared to the particle. B, particle. Oh, these are the cases for his thing. See, somewhere he gives the three reasons, and then he says it's interesting when they all fail. Stokes-Einstein, blah, 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 blah. Anyway, it's in here somewhere, but basically it's got to do with the relationship of the relaxation times and things. And my A and B study monodispersed single spherical. So this is just saying like, just say what I said or say what you think. Basically, if this thing is going to have KT transport, right? It's not going to be like that. I mean, this model isn't helping much for this because these things, first off, they're touching each other. There's an interference between the particles. The drag of one, so how that's going to actually transport through a viscous melt is hard to envision due to KT. And this vision is not helping much with it. So you maybe just compare those two. That's what I was asking. Trying to impact the vehicular stick slip. So he's got these three things that he talks about in the paper, and then how would that impact it? In other words, the vehicular really only works if you have a sesquioxane, so a particle that's smaller, so small it's like a monomer size. And then it can glue to it and ride it like a pony. So the polymers are moving faster than the filler particle, but they can catch a ride on the pony and then they'll release at some point. That's the vehicular model, right? So if you have something like this, there is no vehicular model that's really possible. You can have bound rubber or bound polymer on the surface of these particles, and you have that. That's been shown, but basically how that would affect transport is complicated. And anyway, the size of a single primary particle isn't even important to the transport of the whole aggregate, right? It's a whole object that moves. So anyway, so the slide you could kind of talk about here, think about it. The stick slip mechanism, I didn't really understand. It's in the paper. It's something about the particles get stuck to the polymer and then they release and all of a sudden they like jump. So they jump to another position. I'm not exactly sure what that causes that jumping. And then again, that's for a certain size range and a certain relaxation time ratio. And then the modified Stokes-Einstein, well, yeah, you have bound rubber, it's going to affect the transport. And then the viscosity of the thing is going to be much higher because of the filler particles in it. Um, so the modified Stokes-Einstein could make sense for this. And people commonly use, so in fact, this equation for viscosity that Winey shows is actually, this is written for tire rubber. This is the Guth-Gold equation. They were people that worked for like Michelin or something, right? So their tire company people invented this equation. They don't even cite like origin of that, but basically there's a series of people that kind of came up with this equation, and there's other modifications too. But anyway, so that equation is used like in this industry. So all right, let me just skip through so I can touch on all these. So equation 8 due to Einstein, that's the viscosity thing I just showed you. When asked what work he wished he had done, he mentioned this not done. So he wished he hadn't invented that equation because it's just a displacement law. And then I guess it was below him to do that. So that the first two terms, equation 1, are due to a displacement. So just show how that works. And then the 2.5 factor is a little bit more complicated to calculate. It's for spheres. So, but you just the idea that it would be a volume fraction to increase the viscosity is just the idea that you have a displacement. If I can do that. So if you have the fluid, so you have it's going to be dv dy, and the dv is fixed. That's like your velocity at the top and no viscosity at the bottom. So the dy becomes a smaller number. So you have viscosity dv dy equals the shear rate. So if y becomes a smaller number, then over here, and that just boosts the viscosity. So if y is displaced by this solid fraction, so you have one in the solid fraction, that just boosts the viscosity. And see, just write the equation for viscosity. Say you're going to just displace with the thing that you put in, you're going to get rid of some of the fluid, but you're going to consider that you're looking at the same thing, but you're actually looking at that thing, then you'll get this linear function for the viscosity. Basically this first two terms, you'll get the 2.5 you won't get, but you get the idea that it's one plus the volume fraction that you displaced. Right, so that's just a simple displacement law. Hopefully you can work that out. All these things might take a little bit of effort, but just do the best you can do. Explain the modification of the Stokes-Einstein to yield equation 2. So equation 2 is just that he's substituted or she substituted the effective radius because of the bound rubber, and this viscosity change due to the Guth-Gold equation, the rubber equation, which is also the first two terms of the Einstein viscosity equation. Consider the size of the spherical particles and the two chain size of the velocity. So, all right, so does it make sense? Does that equation make sense? So there's some issue. Anyway, there's some issue about the size scales here. So you should draw realistically like you have a network. So you have some distance, like the tube diameter or the entanglement distance, right? And then the particles, like are the particles big compared to that, or are they little, or are they the same size? So whether that thing works, this bound rubber thing works, depends on how big the particles are compared to the size scale between the entanglements of the system. So somehow you have to kind of work that out. I'm asking you to kind of consider these things, like how do those things, does that model, the modification of Stokes-Einstein still make sense? Like does even diffusion, like thermal diffusion even make sense when you have this kind of system, like so viscous and such large particles? The last thing is like the charges, like this thing I said about SiO2 has strong charges, Al2 has almost no charges. So can that explain what's going on? Can that explain where you see that deviation? And then also the particles are smaller. So the question is like, write an explanation for why that deviates here. And the idea is that at this point, it doesn't depend on the because it's only the absorption, desorption. So you weaken the absorption so much that it starts to have a time scale close to the entanglement relaxation time scale. And at that point, this desorption absorption phenomenon dominates the diffusion coefficient. And that doesn't change with molecular weight of polymer, so that becomes constant. I think that's basically the gist of what the whole Schweitzer whiny thing is going on, as far as I can see. It's more involved than that, but basically that's where it's going from. So anyway, hopefully that'll be all right. So just like email me if you have questions. The ones that I think I had two emails in the last homework, I basically would just answer the thing for you. If just email me if you're stuck on it. Try to do it, and then if it fails, email me. I can try to work through it with you. Okay, so any questions or anything? We're out of time, so okay, so I'm gonna quit there.
Thank you, sir.
Thanks, yeah.